This is the video 2 for fluorescent and bioluminescent fission proteins for neuroscience. In this video, we will talk about engineered fluorescent and bioluminescent proteins. Specifically, we will talk about what is fluorescence, the history of GFP proteins, and how is GFP structured. In very basic terms, fluorescence is the emission of light by a substance that has absorbed light or other electromagnetic radiation. The absorbed radiation usually occurs at a lower wavelength, while the emitted radiation occurs at a longer wavelength, and therefore with lower energy. This also means that the color of the light used for excitation and the emitted light are different. When external radiation is applied to a substance, this one absorbs the radiation and molecule transitions to a higher electronic state. This process is called excitation. This excited state only remains for a short period of time, and after that the electrons go back to their ground state. During this transition, energy is released in the form of emission. This phenomenon is called fluorescence and can go indefinitely over and over. The specific frequencies of excited and emitted light are dependent on the particular substrate. Here there is a list of well-known fluorophores that are used in life sciences that have a specific maximum excitation wavelengths and maximum emission wavelengths. And here there is a link in YouTube where you can know more about fluorescence and how it works in the use of different fluorophores. A fluorescent dye absorbs light over a range of different wavelengths, and every dye has a characteristic excitation range with an optimal for excitation. During emission, every dye also emits light over a range of different wavelengths, having also an optimal for emission. Knowing the excitation and emission spectra of a fluorophore is critical when choosing optimal light sources and filters for your fluorescent microscope, as well as when visualizing more than one fluorophore in a sample. For instance, if the emission spectra of one fluorophore, like CFP, overlaps with the excitation spectra of the other fluorophore, such as YFP, you can photobleach the second fluorophore by continuous excitation from the first fluorophore, and the obtained signal will not be optimal. In addition, if the emission spectra of the two fluorophores that you choose overlap significantly, such as this case for GFP and YFP, the signal of one fluorophore will bleed through in the detection of the other fluorophore and can give you misleading results. So therefore, if you want to detect the signal of two fluorophores, make sure to choose this so that their emission spectra do not overlap, such as the case of GFP and M-Cherry. So one of the most famous proteins, fluorescent proteins known in biology is GFP, and its use in life sciences has become a fundamental tool. The story of how fluorescent proteins like GFP came to be used as research tools is particularly interesting. And although we have known about bioluminescent organisms and their characteristic radiance for several decades, the first time that anyone truly examined what caused this glowing phenomenon was Osamu Shimomura in the 1960s, who studied the bioluminescent properties observed in the crystal jellyfish Aquaria victoria. He observed that on the underside of the umbrella of this organism, there is a ring that glows with a faint green light. To investigate this green glimmer, Shimomura collected many jellyfish specimens from the Pacific Ocean, and he was able to isolate two proteins from the jellyfish photo organs. The first, which he called aquarin, gives off a faint blue light when it binds to calcium ions. And the second is what we know now, GFP, which absorbs the blue light from aquarin and glows green. Then, years later, the work of Martin Chaffee, who was the first in expressing GFP in exogenous organisms such as E. coli and C. elegans, and the biochemist Roger Tsien, who discovered the molecular mechanism of GFP function, culminated in the Nobel Prize for Chemistry in 2008. Since then, many different mutant versions of these fluorescent proteins with different fluorescent properties were generated, and their use revolutionized life sciences research. Regarding the structure of GFP, X-ray crystalline structures of the AVGFP and its homologs revealed that these proteins share a beta-barrel fold comprised of an 11-stranded beta-sheet polypeptide. At the center of the AAV-GFP barrel is the fluorophore. This fluorophore is composed of modified amino acid residues within the polypeptide chain. This is a very unique property of GFP because many other fluorescent proteins have a fluorophore as a separated prosthetic group. However, in the case of GFP, this fluorophore belongs to its own polypeptide chain. This unique structure is what gives the fluorescent characteristics of GFP. In this last slide, you can find a short quiz that summarizes some of the most important concepts for this video that we will also see in class.